Humanity has finally traveled to distant planets, and this guy here, well, he wants to know the acceleration of gravity on this new planet X. But his device that measured gravity, or the acceleration of gravity on new planets, well, it fell out of the spaceship on the way here. So he needs to find the acceleration of gravity somehow else, and all he has is a pendulum, a timer, and a meter stick. Will he be able to find this acceleration with nothing but his brain and these three tools? Let's find out. In lab number 3, we were assigned to find the acceleration of gravity with nothing but the pendulum I mentioned earlier, the meter stick, and that timer. Now, basically, we wanted to record the length of this string, and for clarification, a pendulum is just a weight on the end of a string that oscillates back and forth. We wanted to record the length of the string for different periods. And so, for example, let's pretend that we had one period, so it oscillates this way and then back, of 0.9 seconds. So it takes 0.9 seconds for it to swing here and swing back. But that's kind of tough to measure. So instead, we multiplied that by 20 oscillations, and we got something of a period equals 18.0 seconds. So basically, we recorded it oscillating 20 times and wanted to get it as close to 18 seconds as possible, and adjusted the length accordingly. Adjusting the length would allow us to change the period, which would allow us to try and get really close to that target of 18 seconds. But this isn't the only target we had. We had a bunch of periods that we had to get, and you'll see the data later. But I hope this all makes sense, that basically we're just measuring the length of this pendulum to derive the acceleration of gravity, and we'll get to all that later. Also, it's good to mention that the mass on the end of the string has no impact on the period of the pendulum. To start, we found a convenient metal dowel above the floor that was attached to one of those chemical washing stations in case you jump in a vat of acid, and attached the string in such a way that we could adjust it to adjust that period. And then we attached a weight on the end and started with our first period of 0.9 seconds, and then recorded 10 of those total periods to get an average. And then we measured the length of that string to the center of the mass, and then moved on to 1.0 second period and then 1.1 second period, all the way to a 2.4 second period. So it's 16 periods total. And all of that gave us this set of data. Now, if you're wondering why there's a bunch missing, it's because we ran out of time and needed to finish, so we just kind of skipped to the end and called it good. Now, I know this is pretty complicated, so here's a set of our average periods, but in order to find the acceleration of gravity, we couldn't use our total period, which was 20 oscillations. We only wanted the period of one oscillation. So we had to take our average time and divide it by 20 to get the time for one oscillation. And that's what you see here, paired up with all of the measurements that we measured from the start of the string to the center of the mass. When plotting the period versus the measurement of the string, we arrived at an exponential graph. Now, we wanted a linear graph, and so we achieved that by squaring the period and then comparing that to the length of the string without squaring the length of the string. And this gave us a linear graph, which is what we wanted in our equation to derive the acceleration of gravity. And this is going to be accomplished through a dimensional analysis, and that's what we're going to do right now. So what you just saw is a linear graph with a bunch of points on it that has a straight line. And we know that the equation of this line is y equals mx plus b. However, at zero time, or zero length, your y-intercept is going to be 0, so we can just kind of cross out b because we know it's 0. So y equals mx. With that, we're going to plug in our units, and y is going to be our time, t squared, and x is going to be our length. So we're going to plug that in, t squared equals m times l, and now we're going to find the slope here. And we know that slope equals the difference in the y's, the endpoints, divided by the difference in the x. And when we plug in those endpoints that you saw in the data, the average data, this is, this is 5, 0.77 minus 0.81 divided by 1.469 minus 0.2061. And m equals 3.93. So we have a linear graph here, and t squared equals m times l, but in this linear graph, t squared is proportional to l. So we're going to write t squared is proportional to l. Now in order to make a proportion in equation, you have to add a constant. So I'm going to multiply the left side by g, because g is one of the constants in the pendulum, the acceleration of gravity, and which doesn't change, which means it's a constant. So I'm going to add it here, and I'm just going to put it in its units form. So meters divided by seconds squared times t squared is equal to L. And I'm going to divide both sides, and I get t squared equals L over meters per seconds squared. And now we're going to go back into our original equation here and say that t squared equals m times L over meters per second squared. And now we're going to plug in our slope, and we're going to plug in the actual acceleration of gravity in a way that cancels out to equal 0. So we have t squared equals 3.93 times 9.80, the acceleration of gravity without its units, times L. And this is all over now this is the acceleration of gravity, 9.80 meters per second squared. I'm running out of room here, so I'm going to erase everything with my very colorful rag. So we had t squared equals 3.93 times 9.80 times L over 9.80 meters per second squared. We're going to multiply these two top things together to get t squared equals 38.5 L over 9.80 meters per second squared. Now this is when a little bit of the magic of labs comes in, because this number we noticed is very close to 2 pi squared, which equals 39.4. So I mean, I'll be honest, in order for this whole thing to work, you have to use this value. It turns out to be this, not what we got here. So our results in our data were a little off, but that's okay, because this is the actual value we want, and we're going to substitute this for that now and say that t squared equals 39.4 L over 9.80 meters per second squared. And it's important to note that this is actually 2 pi squared and not 2 times pi squared, which would give you 39.4, just in case that caused any confusion there. And also, I'm just going to rewrite this and substitute g, just the little letter g, and call that the acceleration of gravity. So I'm going to say that equals 39.4 L over g. So now we have t squared equals 2 pi squared times L over g, and we're going to solve this for g here, and that's pretty easy to do. Just multiply both sides by g and then divide both sides by t squared, and g equals 2 pi squared times L over the period squared. The really cool thing about this equation here is that it can be used to find the acceleration of gravity on any planet in the universe. It's not just Earth. Now I'm going to solve for g here with a couple of our points just to prove that we get something around 9.80 meters per second squared, just to prove that this equation does indeed work. But I think it's fun to realize that this equation works anywhere in the universe. Anyway, we're going to do that now, plug in a couple of our random points. It doesn't really matter, they just have to be a pair. And we're going to say that g equals 2 pi squared times 0.3625 meters over the period squared. For this one in our linear graph, the period squared was 1.44 seconds. And that gives us a value of 9.94 meters per second squared, which is really, really close to, we'll do a little squiggly for approximately 9.80 meters per second squared, and that is good. But this number here is still a little off from what we would have really liked to get, so now we can start talking about why that might be the case. So where did this error come from? Well, in our measuring method, even though we had very consistent data and very precise data that gave us a very nice linear graph, we were probably inaccurate in a little bit in our measuring method. So we were consistent in that inaccuracy, which gave us something maybe a little like 1 to 2 centimeters off. Also, there was the circumference of the dowel, which may have played a role in the string wrapping around the dowel as it swung back and forth, and I'm not sure if this would have a huge impact on it, but it certainly could be a factor. And now, how would we improve this? Well, we could get much more data, be more accurate with our measuring, and use something maybe like a fishing pole or like just a fishing reel to just use very small increments in increasing or decreasing the length. To sum, by setting up a simple pendulum, timing several oscillations of different lengths, and employing the slope-intercept form equation, we were able to find an equation that could be used to calculate the acceleration of gravity on any planet. And even though our methods and equipment could have easily been refined, we still arrived at a conclusion that was fairly close to the true value that we were hoping to get.